Hello dear students, welcome to the channel and welcome back to this playlist in which we are discussing about sampling and reconstruction of my signal. So in the very first video of this playlist, if you haven't checked it out, please check it out. The link will be flashing on the top right hand side corner of your screen on the I button. In that lecture we have studied about uh, basics of sampling, what is actually a sampling, and we studied about sampling theorem, and we studied about the implications and try to prove the sampling theorem. We understood the sampling process in deep, and also we discussed about the low pass and band pass signals very briefly. So today we are going to discuss about the recovery using the ideal low pass filter. So earlier, if you remember, in the previous class we have studied about low pass filter, and today we are going to discuss about the recovery of my signal using that low pass filter or low pass signal, you can say. So earlier we discussed about reconstruction in very short detail as well. So you know that reconstruction or recovery is the process of recovering the original signal from the sampled version of that signal, right? Like you can say I'm recovering x of t from x delta of t. So here, as you can see in this image, x of t is my original signal and x delta of t is my sampled signal. Reconstruction is the process of acquiring my original signal from my sampled signal, as you can see in this image, and that is the block diagram of it. So for this sample signals, x delta of t is the process through an ideal low pass filter which gain t and cut off the frequency greater than omega, right? So what do? We simply process the signal. We cut off the frequency greater than some omega value and keep the frequency only in range, right? So and also the ideal low pass filter is called reconstruction filter as well. So just so you know that actually ideal low pass filter is also called reconstruction filter. So the filter which we use uh, in recovering of my signal is also called reconstruction filter. Now when the sample signal x delta of t is applied to the input, this filter will allow only this shaded portion. I'm sure you can see this shaded portion from minus omega to plus omega. This is not w, this is omega. So book is having some errors. So I've mentioned it in previous class as well. I'm mentioning it again. It is omega, it is not w. So from minus omega to plus omega, that portion is shaded, as you can see. And the filter will only allow this shaded portion in the spectrum of x delta of t to pass through the output, and it will block all other frequency components thoroughly. So the frequency components only will correspond to the x of t will be passed through to my output, and the original signal x of t will be recovered. However, the ideal filters are generally not used in the practice for so many different reasons. Let's say if I'm having some practical applications, the ideal filter, the ideal low pass filter, will be replaced by a non-linear filter, right? And non-linear filter is, by the way, represented by h omega, and that approximates the desired frequency characteristics with sufficient accuracy, right? So h of j omega will be very close to 1 for all the values of omega, and except there it will be 0. And due to such approximations in the low pass filtering stage, some discrepancy is expected to exist. between my original signal and recovered signal, right? Because you cannot acquire it as perfect as it was earlier, right? So we need to select non-ideal filter based on the acceptable level of distortion for all the applications under the consideration, right? Now let's see what is the sampling with the zero order hold. This is not recovery actually, this is sampling. Let me correct it. Okay. So sampling with zero order hold, and I'm going to put it everywhere. Okay, we don't want to keep the older one, so we are going to delete it. Here you go. Okay. Okay, we are having one more here, so let's delete that as well. We'll keep only this. So we are going to discuss about the sampling with zero order hold. Then later on we will discuss about the first order hold as well. So earlier we studied sampling theorem, and if you remember, it explains in terms of impulse train of the samples, right? And it proves that the band limited signal is uniquely represented by number of different number of samples. But in practical scenarios, what happens? It gets very difficult to generate and transmit that narrow large amplitude pulses which approximate impulses, right? And because of that, it is more convenient to generate the sample signals in form of referred to as zero order hold. Now what is zero order hold? So this zero order hold, this type of zero order hold system samples the the input x of t at a given instant and holds that value until the next instant at which sample is taken, right? Let me repeat it. The zero order hold system samples the input x of t at given instant, and it holds that value until your next instant comes up at which your sample can be taken. So as you can see, later on we will be studying quantization as well. If you understand the zero order hold and first order hold very well, then you will be able to understand quantization very well as well. So this is my original signal. Now see, it is holding its value till a certain extent. See, it's holding its value certain extent, then it is one. See, it is trying to follow it. It is a square wave, but it is trying to follow it. So the reconstruction of my signal, let's say I'm having x of t. As you can see, this is my original signal x of t. From the output of zero order hold can again be carried out by low pass filter. But again, as you can see in this case, uh, the required filter, it must not need to have constant gain in the pass band, right? And this type of signals, when we use the zero order hold technique, we are having some characteristics related to my filter. So what are these characteristics? So first, in order to develop the required filter characteristics for the zero order hold system, my output of this as you can see in this block diagram, zero order hold is normally generated by impulse train, which is impulse train which takes samples followed by LTI system with the rectangular impulse responses. As you can see here, we are taking rectangular impulse responses, and it shows the input signal x of t is sampled by a train of impulses, right? Remember, if you remember in the remember from the previous class, we called it s of t. So the train of impulses s of t to produce the sampling signal x delta of t. After that, the signal is passed through. Let me show it from here. as you can see here. First my original signal, here comes the impulse train, here is the output of multiplication, or rather call it sampling of my signal. This signal is passed through the LTI system with impulse response h0 of t. This is my LTI system with impulse response h0 of t, in order to produce zero order hold sample signals, right? Which means my final signal, this. And it will have, again, it will, how much frequency it will have, the frequency response will be hrj omega. So let me show you this way. This way it will be more clear to you. See, first I'm having a first I'm having my signal x of t, then here I have impulse, train of impulses, and then I'm having x0 of t using zero order hold. Now things can be a little bit different for cascaded system. So what can come here, let's see. So see this image, the first one, it shows the cascade of zero order hold on system with reconstruction filters. So here the transfer function hr j omega of this system should be such that the recovered signal r of t will be equal to my original signal x of t. Right, here I'm having original signal, here is the output signal, and rest the process is same as you can see here. It's just this is a cascaded system, right? And as I've said, r of t should be equal to the original signal x of t if cascaded combination h of t and hr of t is the ideal low pass filter h j omega with a constant gain, right? So if the recovered signal r of t would be same as the original analog signal if the cascaded combination of these two h0 of t and hr of t is the ideal low pass filter h j omega, as you can see here, with a constant gain. The gain of this should be constant. Then the transfer function equation has been given. If you have studied the control theory in detail, you must be able to find out how you find the transfer function. If you not, I'm not going to explain that in detail, but we basically divide the output by input, right? Our transfer function of output divided by transfer function of input. So here we get it. And in order to make this happen, make my output signal equal to input signal, this equation or this expression must be satisfied. hr of j omega must be equal to e raised to j omega t by 2 h j omega divided by 2 sine omega t by 2, whole term divided by omega. Let's say for example I'm having a cutoff frequency of h j omega which is equal to omega s by 2, and the ideal magnitude and phase responses for this reconstruction filter, which follows zero hold, will look something like this, right? Omega by 2, omega s by 2 minus omega s by 2 plus omega s by 2, hr j omega, correct? Now in practice the frequency response in this formula cannot be exactly realized, right? And because of that we need to design an adequate approximation to it, right? You need some approximation. So in many situations what do we do, the output of the zero hold is uh, the output of this zero order hold itself is considered an adequate approximation to the original signal without any additional low pass filtering, no additional low pass filtering. In other words, it represents a possible but still very coarse interpolation between sampled values, which you can see here, correct? And alternatively, in some applications, a smoother interpolation between sampled values may require. So now we are going to discuss what this interpolation is and what significance does it holds, right? So let's see the interpolation. So what this definition says: the interpolation is the fitting of the continuous signal to a set of sample values, is a commonly used procedure for reconstructing a function either approximately or exactly from samples, right? So either approximately or exactly we are what we are doing, reconstructing the original sample by taking sampled values. See, this was my original signal. As you can see here, the dotted signal is the original signal, and then here I'm having the reconstructed signal with the help of interpolation. Here the dots, the darker dots are the sample values. See, so this one is called linear interpolation between my sample points. And as I've said, this is called linear interpolation. That what does it mean? It means interpolation had different number of types. So basically, it has two types. We can call it. We can use it to reconstruct signal from its samples. First one is the zero order hold, which we just studied a minute ago. Another one is called the linear interpolation, or also known as the first order hold. So the simplest interpolation procedure is a zero order hold, which we discussed earlier, and then the second one is the linear interpolation or the first order interpolation, which you are seeing in this image. This is the first order interpolation, right? It's we are in zero. What do we do? We take square waves. Here we are taking line, right? The dashed curves to be precise, right? And these dashed curve represents the original signal, and then this solid curve, the line, is representing my interpolation. um, Actually, in more complicated interpolation formulas, the sample points may be connected by high order polynomials of other mathematical functions, right? Because we are taking only first order polynomial, here we are having straight line. If I want to have curve exactly like it, I will need a higher order polynomials, right? And it will make things a little bit complex, so we are not taking it. If it is absolutely necessity to take it, then we can take it. So we have already seen in previous section for band limited signals, if the sampling instants are sufficient close, then the signal can be reconstructed exactly by using only the low pass filter, and we can carry out this exact interpolation between the samples using this. So the reconstruction of my original signal, let's say x of t, is a process of interpolation that makes it clear. And when we consider the effect in the time domain of my ideal low pass filter, we can find the output of low pass filter, right? And that output is given using this formula: xr of t is equals to x delta of t into h of t. Actually, not into, it is actually what we call convolution, but uh, we can also say it that way, right? Remember the previous properties when we discussed the properties of sampling as well. Now with x delta of t is given using this formula, x delta of t is given using this formula, summation n equals to minus infinity to infinity x of n ts h of t minus n ts. This equation is telling us how to obtain the continuous curve between sample points x of n of t, right? And also this is the formula for interpolation. Now, if you don't know how we can find the impulse response in the ideal low pass filter, the formula of it is also given here. H of t represents its formula, so you can find out the impulse response as well using this formula. And when we substitute the value of this h of t, this whole term here, what do we get? We get this equation, right? And this equation is representing the interpolation using impulse response of an ideal low pass filter. Basically, we are taking summation minus infinity to infinity. The first term is remaining as it is, x of n t of s, and instead of the value of h of t, we have to take the value of h of t minus n ts. So we will find omega c into t divided by pi omega c ts sine omega c t minus n t divided by omega c t minus n t. This will be the whole term, and it is representing the interpolation using the impulse responses of an ideal low pass filter. And one thing, I let me make it very clear: the reconstructed signal according to this equation will be omega c equals to omega s by 2. Remember, we took it earlier from here. Yeah, we took it omega c by 2 or omega s by 2, right? Now let me show you one more image. See here, in the first one image, it is band limited signal. So first one, the band limited signal is showing us the original band limited signal x of t. The second one is representing the impulse responses or the impulse train of samples for my original signal x delta of t. And the third one, the figure C, is drawn by the superposition of individual terms in this equation, right? In this equation. So the interpolation using the impulse responses of an ideal low pass filter is commonly known as band limited interpolation. And because here what is happening, my original signal x of t is a band limited and the sampling frequency is satisfying the conditions of the sampling theorem, we can say that in many cases it is preferable to use less accurate but still simple filter, right? Which gives us simple interpolation function and gives us easier outputs. Let's say, for example, zero order hold can be viewed as the form of interpolation between sample values in which the interpolation function h of t is the impulse response, which is plotted in the form of h0 of t. And in that sense, x0 of t is the figure corresponding to the approximation of x of t, and the system h0 of t represents the approximation to the ideal low pass filter required for an exact interpolation. So basically, see this image, it is showing the magnitude of the transfer function of the zero order hold interpolation filter uh, superimposed on the desired transfer function on the exact interpolation filters. So this image, in this image we can see that the zero order hold is in the very rough approximation, although in some cases it is sufficient enough, so you can still use it even though it is in very rough approximation. You can still use it in so many cases, and that is why in so many cases it is actually used. Zero order hold is actually used. Now we talked about the reconstruction using zero order hold, the first order hold, or interpolation. Let's talk about the reconstruction of a signal using IFT, or inverse Fourier transform. So we let's say we can obtain our original signal x of t by taking the inverse Fourier transform of my signal. If you remember, how does the Fourier transform works, right? Frequency to time, time to frequency. You can it allows us to move from one domain to another. So by taking inverse Fourier transform, you can gain your original signal back. And if you remember what was the formula of inverse Fourier transform, here we have 1 by 2 omega, because my original signal is getting divided by 2 omega, so we will write outside the bracket 1 by 2 omega. Inside the bracket you will have summation n equal to minus infinity to infinity into my original signal, which is x of n divided by 2 omega, into e raised to minus j pi f into n divided by omega. Actually it was minus 2 j pi f, but sorry, the whole term divided by 2, but we already having divided by 2, so 2 will get cancelled. Sorry, multiplied by 2, not divided, my mistake. Now using the definition of inverse Fourier transform, we can take the integration, and by after interchanging changing the order of summation and integration, what you will get, you will take these terms out, you will keep only these terms in, and when you take the integration of e raised to whole term, what you will get, you will get the whole term 1 by the whole term multiplied with my original e raised to whatever, let's say the whole multiplied term is p, so e raised to p, and limit will be applicable minus omega to plus omega. And when you put the limit here, what you will get, you will get final formula which will look something like this, right? Basically you will get this function, but this is basically the sinc function. If you have studied the sinc functions in the mathematics or calculus classes, this is the sinc function. So you can represent it using this formula, x of t is equals to summation n equal to minus infinity to infinity x n divided by 2 omega sine 2 pi omega t minus n omega n pi divided by the whole angle 2 pi omega t minus n omega, right? So you can also call it a sinc function, which is defined as sinc c, sinc of x is equals to sine n pi into n pi, or sine pi x divided by pi x. So such way you can write this equation using this formula as well. Instead of writing the whole term, you can simply write the sinc function. So as we saw earlier, there is a formula for interpolation for the reconstruction of the original signal x of t from the sampled values. The sinc function will play the role for interpolation function as well, and each sample x of n divided by 2 omega is multiplied by the delayed version of the interpolation function, which is also happens to be sinc function, and then all these resulting waveforms are added to obtain my original signal x of t. Now when you add all these values, what you will get is, will look something like this. Wait, yeah, it will look something like this, right? So when you add that, this function will be formed, and when you expand it, it will look like this. I'm not going to explain it again, I think I've explained it in previous lectures as well. So see here in the first term, which is x0 sine sinc 2 omega t, this function will have maximum amplitude at t equals to 0, and the maximum amplitude will be equal to the sample value x of 0 at t equals to 0, which means the sinc function will pass through the zeros at t equals to which value? See here, the first term, right? It will pass through plus 1 by 2 omega plus 1 by 4 omega, right? Which you can see in uh, this image here. Then the second term, what was it? Let's go back and see. Yeah, x of plus or minus ts sinc 2 omega t plus or minus ts. So the second term will have maximum amplitude at t equals to which value? C, plus or minus ts, right? And the maximum amplitude will be equal to the sample value of x of plus or minus ts at t equals to plus or minus ts. and thus the sync 2 omega t plus or minus ts will represent the shifted sync function, right? Sync 2 omega t, you can see, and the period will be plus or minus ts, which is also visible here, right? Here and here, first one, here you are having the second one, right? And similarly the third one, uh, and all the remaining terms. The third term is x of plus or minus 2 ts sync omega 2 omega t plus or minus 2 ts. It will represent the shifted sync function sync 2 omega t by a period of plus or minus 2 ts, and so on. And we can plant it all, so you can see the planted everything here. Here we are having the reconstructed signal x of t. As you can see, it is getting reconstructed like this. Here are the sample values in the dot, and here is my sync function, see, right? So you can plot it that way, but note that the peak amplitude of any sync function is equal to the corresponding sample value of x and of ts. So the actual reconstruction with low pass filter, as you can see in this image, that the peak of the sync pulse will represent the amplitude of samples. The signal x of t is expressed in previous equation, in this equation. Hence the sampled signal is there then passed through the ideal low pass filter in order to recover the original signal, and this low pass filter is therefore called as reconstruction filter as well, right? So it is a reconstruction filter as well. Now let's see the first order hold or linear interpolation. So in crude interpolation, what did we do? Let's say if we have zero order hold, if it is not sufficient, then we have to use the first order hold or the linear interpolation, right? Or you can use variety of smooth interpolation strategies as well. So except for first order hold, we are having higher order holds as well. So the zero order hold will produce an output signal, as you can see with discontinuities, as we saw earlier as well, right? We earlier saw it was taking the square wave and there were so many discontinuities in that. So instead of these discontinuities, let me show it to you one more time. Not here. See, it is having square wave, so there are so many discontinuities. Actually, you cannot even tell that this is the reconstruction of original this signal, right? So in order to get rid of that, what do we do? We come back to first order here. Yeah, the linear interpolation is what we choose, and as you can see here in this image, what do we do? uh, the reconstruction that are continuous, although with discontinuous, not discontinuities actually, but discontinuous derivatives due to the changes in the slope at the same sample points, we get rid of it. The linear interpolation is sometimes called the first order hold on or first order hold, and it can also be viewed with the triangular impulse response h of t, right? The triangular impulse response, you can see here we are having impulse train of c, as we have the inverse train of samples, we can have the inverse response representing the first order hold on with triangular impulses. See here, so many of them, right? Now when you take this triangular impulse responses, the associated transfer function is also shown in the figure. See, h g omega equal to 1 by t sine 2 omega ts divided by 2 divided by omega 2 whole square. Apologies, as you can see in this image. So the transfer function of the first order hold on is shown superimposed on the transfer function for the ideal interpolating filtering technique. And in a similar manner, we can define the second and higher order holds that produce reconstruction with a higher degree of smoothness. So if you want more smoother image, go for higher order, and by doing that you will be able to acquire that smoothness. But in process, the calculation will get a little bit more complicated, and that is why we don't actually often use it so much. In upcoming classes, we are going to discuss my favorite topic, aliasing. If you are into computer vision, this topic would be very important to you. Or even in image processing or computational photography, aliasing is very important. We're not going to discuss about the aliasing of images because that would be 2D. We are only going to discuss about the aliasing in 1D. So uh, if you are into that computer vision, image processing, computational photography and such stuff, next lecture is for you. We will wrap this lecture here. If you have any doubts, any queries, or if you want to connect with me, please mention in the comment section below. Any type of feedbacks are welcome. Please mention them in the comment section below. I will be seeing you next time with aliasing and more important stuff like that. So until next time, thank you very much for listening, and I will be seeing you next time. Thank you. Goodbye for now.